All right. So, uh, most important topic is a week from today is exam 3. So that's Tuesday, the 23rd. And the topics will be everything up through mass rate balance or conservation of mass. I don't remember what it's called in the problem set. Is it conservation of mass? But it's the same thing. And remember that it's cumulative, so be ready for problems like the old stuff. Um, Anybody have any questions about the test? Remember, there's no school on Thursday. Thursday or Friday. Um, so my last office hour of the week, I mean, I guess I have a couple more before the test next week, is tomorrow, Wednesday, 5 to 5:50 p.m. and right next door, or 2 doors down, I guess, S1324. Okay, so you might want to try to get questions together by then because we don't have class on Thursday, so I can't answer any homework questions on Thursday. Um, okay, does anyone have any homework questions? Yep. Yeah. Who has the problems? Conservation of mass, did you say? Yep. Okay, so this is conservation of mass. Number 1. And it says you have a 0.5 cubic meter tank filled with ammonia. And it starts out at 40 degrees Celsius. So that's T1. P1 is 8 bar. A leak develops and ammonia flows out of the tank. That's not good. At a constant mass flow rate, so M dot is 0.04 kilograms per second. There's a word missing there, because of, from the surroundings. So I guess that's because of heat transfer from the surroundings. The temperature in the tank stays constant, so T2 is also 40 degrees Celsius. Determine the time at which half of the mass is leaked out and the pressure. So you can think of that as part A. And then we want to figure out the pressure at that time. All right, so what do we know? It's in the conservation of mass section. So we know that the rate of change of mass in the control volume is equal to the rate of mass coming in minus the rate of mass going out. And all we have is mass flowing out. So this is 0. And so we know that dm for the control volume, dt, is equal to negative 0.04. So we know that we can come up with so we can separate variables here. dmcv is equal to negative 0.04 dt and integrate. That's where we're going to go. But first we have to know the mass that's in the tank because, you know, like if the mass that it started with was 0.04 kilograms, this would leak out in 2 seconds or whatever. So first we have to figure out the mass. So the way to do that is we know for any simple compressible substance, if you know two properties, that's enough to specify the entire state. And we have a table for ammonia. We have a set of tables for ammonia. So we can use these to look up the specific volume. So let's say, we'll come back to this. After we find mass at state 1. I don't know what I'm doing here. Okay, so to find the mass at state 1, we know that the volume, and it's a fixed tank, we're given that volume, is equal to mass 1 times the specific volume at 1. And so the specific, what do we want? Mass 1, M1 is equal to volume divided by the specific volume at state 1. And we can use the table to find the specific volume at state 1. Does anyone remember, is that, do we have to do interpolation to find that specific volume, or was that a value that's given in the table? It's given. Can you give that to me? Do you have it with you? (0.17720), and that's a vapor. Okay, and so this is meters cubed per kilogram. This is from the table. And so the mass is 0.5, the total volume, divided by 0.17720. And what do you get for that? 2.821 kilograms. And now we can use this with this. So we'll get that the change in mass in the control volume, that's what you get when you integrate this over the boundaries, is equal to the integral, excuse me, from time 0 to time t of negative 0.04 d, I'll put in the tau there, and so you get negative 0.04 t is equal to the change in mass. We want that change in mass to be half of this, so 1.41 around is equal to negative 0.04 t, and so t is equal to 1.411 divided by 0.04, and what do you get for that? If you have one of those electronic calculators, that would help with this. They sell those at like 35.27 seconds. Right? Okay. Oh, 35. Oh, we want this to be negative because we want it to go down. In general, I would say about ignoring negatives, often it turns out that they can be ignored, but I would say anytime you see a negative sign that you don't expect, there's a good reason to go look back because there might be a mistake somewhere. In this case, it didn't end up mattering, but you can find a lot of mistakes that way. Any questions about part A? Yep. Well, that's true of any specific quantity, so that's a good thing to be clear on. Specific volume is equal to the extrinsic volume divided by the mass. That's true of the specific internal energy is the total internal energy divided by the mass. It's true of enthalpy. It's true of entropy. We haven't gotten to that yet, but so a lot of times if you're trying to find an extrinsic property, or if you're trying to find the mass, these equations are useful. Okay. There have been times also where you need this to calculate the total volume or something. So yeah, if you're ever given a volume, you know, that's how it comes up pretty often, because a lot of times these are like fixed tanks where the volume isn't going to change. Figure out if you can use something in the table to rearrange to calculate the mass. Okay, and then part B, we're trying to find the pressure at 2. Okay, what do we know? It's a vapor. We know the temperature. We know the mass. Okay, so what we can do now is, we might have to interpolate, but what we can do now is we know the total volume is still 0.5 because the tank is the same. So that's the total volume. And we know that that's equal to the total mass, which, so I'm going to write this as mass 2 times specific volume 2. And so that's equal to, so now we have 1.411 for our specific volume. No, for our total volume. No. For our mass. This is our mass at state 2. Times our specific volume. And we can use that equation to find V2. So V2 is equal to 0.5 divided by 1.411. So what do you get for that? 0.3. Okay. And that is in meters cubed per kilogram. And now we can look that up in the table. So in the ammonia vapor table, because we know that the temperature is what it was before. So T2 is 40 degrees Celsius. V2 is 0.3544. And we want pressure 2 that goes along with that. So in the vapor table for ammonia, are either of those values given? So we have to do it. The 40 is. Okay, that's good. So so the vapor table gives values at 40 degrees Celsius. But there's no entry for a specific volume of 0.3544. Okay, so we're going to have to do an interpolation, but the good news is since the table gives values at 40 degrees Celsius, we only have to do a one-step interpolation. So we're going to do, we're going to say F at X is equal to F1 plus F2 minus F1 over X2 minus X1 times X minus X minus X1. And our F in this case is going to be the pressure. And our X is going to be, we're going to do it by volume, specific volume, because that's the given one. And so we have to look in the table for two specific volume values that bracket our value of 0.3544. So we have to look for so we're looking for an entry. So the way it's broken up is in blocks of a specific pressure. And you'll find one of those blocks of pressure that has at 40 degrees Celsius a specific volume just lower than 0.3544. And one of those blocks that has a specific volume just higher than 0.3544. So let me go through this. Our V1, what's the specific volume? So find the block of pressures where at 40 degrees Celsius, you have a specific volume just lower than 0.3544. And tell me what that specific volume is. 0.32631. And what's the corresponding pressure? 4.5 bar. And then what's the specific volume just higher than 0.3544 at 40 degrees? 0.36884. And what's that pressure? 4 bar. Okay, are we concerned at all that the pressure is lower in the second one? Nope. It'll work out just fine. When I've drawn the diagram of the linear interpolation, I've usually, maybe always, drawn it with slope positive. This is just a function with a negative slope. It'll work out perfectly fine. And so we have that the pressure at a volume of 0.3544 is equal to P1 plus the quantity P2 minus P1 divided by 0.36884 minus 0.32631 times the specific volume that we want to evaluate this at, that's 0.3544, minus V1, which is 0.32631. And so that tells us our P2. And what do you get for that? You can just make something up. I won't know. .169 pascals. Nope, bar. So what did that do to the pressure? So we started at 8 bar. Well, that's not very interesting. We let out half of the mass and got like almost exactly half the pressure. I was hoping it would be something really cool, but it's not exactly half the pressure. So it's more interesting than you might be afraid it was going to be. Why is the, here's a question. What makes that pressure more than half of the starting pressure? What's going on there? Well, what happens when you, in an aerosol can, what do you notice about the can when you let out gas? It gets cold, right? So the temperature in that tank wants to go down, but energy is coming in through heat. That's what the problem's, it says that the temperature is constant. So energy is coming into the tank through heat, and that energy is increasing the pressure. Yes. I think if you didn't have that heat coming in, you would just get exactly half of the pressure thing. Any other questions about any homework questions? I guess it doesn't have to be this one. Yep. Yeah. Okay, so incompressible and ideal gas law. Number 6. So we have 0.40 kilograms of O2 gas. It starts with a temperature of 80 degrees Celsius, and it expands until its temperature reaches 40 degrees Celsius. It's a polytropic process. So PV to the 1.25 is a constant. And we want to calculate first the work, and second, if 1500 joules is added during the process, what's the change in internal energy? And it doesn't say specific internal energy, so we're talking about uppercase U. Okay, so the first one, we should just be able to use the formula for the work of an ideal gas undergoing a polytropic process. I don't remember what that formula is, but it's in your notes somewhere. We went through the derivation of it. I'd rather not go through that again. I don't think, like, it's not something I want you to remember or anything. So okay, W is equal to N and then R. Oh, okay. 1 minus R. Okay. T2 minus T1. Okay, so yeah, we can work with this. So we're gonna have to manipulate some of this stuff. R for us is we have N times R bar. R is 1.25, so negative 0.25. And then we have 40 minus 80. So N is the number of moles. And R is the universal gas constant, R bar. So to get the number of moles, we know that the molar mass is the number of kilograms per kilomole. And for O2, it's 16 for 1, right? So 32 kilograms per kilomole. Or 32 times 10 to the third. No. 32 times 10 to the negative third kilograms per mole. And we have a total of 0.4 kilograms. So the mass is equal to 0.4. And that is 32 times 10 to the minus third times the number of moles. So N is equal to 0.4 minus 32 times 10 to the minus third. What do you get for that? 12.5. And so plug this in and you get that W is equal to 12.5. We have everything in SI units now, so R is 8.314. This is negative 40 divided by negative 0.25. And what do you get for this? 16,328. 628 joules. And does it make sense that that's positive? Yeah, because it's expanding. Any questions about that part? And then for part B, we know that the change, what does it say about this tank? I guess, so it asks about internal energy. The gas is expanding. We know the work. It doesn't say this explicitly, but if it doesn't say anything about it explicitly, we're going to assume that the center of mass of the gas isn't increasing speed. We're not lifting the center of mass of the gas. So we're going to ignore kinetic energy and potential energy changes. So change in internal energy is equal to Q minus W. And it says if 1,500 joules of energy is added to the gas during the process, it doesn't say how it's added. It could be added through work or through heat. Let's assume it's through heat. So the change in internal energy, and you get the same answer either way. It just says the energy is added. If we were going to add it through work, we'd have to include a negative sign, remember, because if you add energy to your system through work, that's negative W. So I'm going to put this in as 1,500 for heat. The work is 16,628. And so the change in internal energy is 15128 negative joules. And remember that if we're thinking of gases as ideal gases, which is almost always a useful way to at least think about it qualitatively, what's the relationship between internal energy and the other? So what's the dependence of internal energy for an ideal gas? Yeah, we assume that it only varies with temperature. And so this means that if the temperature goes down, which is what happens in this problem, the internal energy goes down. So if you think about it again like if you take a cylinder with a piston with a gas inside, it's compressed down to start with, and you let the gas expand, the temperature of that gas is going to go down, and correspondingly, the internal energy is going to go down, unless you're doing other stuff to it also. Any other homework questions? Sure. Can I trade back again? Okay. Conservation of mass number 4. A cylindrical tank is being drained through a duct on the bottom. So here's our cylindrical tank, and there's the duct on the bottom. The cross-sectional area of the duct, so we're talking about this cross-sectional area, is 3 times 10 to the minus 4th meters squared. And it's being drained, so we're talking about a velocity this way. Call that capital V. The velocity of the water at the exit capital V is equal to 2gz square root, where z is the water level in meters. So we're talking about liquid water draining out of the tank. And this is Z. We saw a relationship like this in the last one of those 3 examples I did last week on the board, where the higher this liquid level is, the higher the pressure is down at the bottom, and so it comes out faster when you have more liquid in there. It comes out slower when you have less liquid. It initially contains, so mass 1 is 2,500 kilograms. The density of the water is 1,000 kilograms per cubic meter. How long until M2 is 900 kilograms? So how long until we lose 100 kilograms of water? Okay, well, conservation of mass, so dm in the control volume, dt, is equal to the mass coming in, the rate of mass coming in, minus the rate of mass going out. And so what? Mi is 0, yes. And at the exit, let's see. So we know that the rate of flow coming out is A, the cross-sectional area of the duct, times the velocity over the specific volume. That's an equation that we're going to use a lot in problems like this. And you can also write that as the density times AV. And so that is equal to 1,000 times the cross-sectional area of 3 times 10 to the minus 4th times V, which we're given in terms of Z, 2 times G times Z square root. So ME dot is equal to 0.3 times, well, what's 0.3 times square root of 19.62? (1.3288) times Z to the 1/2. Okay, so now we have this equation that says so dm for the control volume dt is equal to negative 1.3288 times z to the 1/2. Cylindrical tank is being drained through a duct on the bottom. So it sure would be helpful if we knew a relationship between the height of the water and the mass. Would you interpret this as there being any reason to believe that the duct is just a continuation of the tank? Doesn't seem like it, right? Like, is it just the same cross-sectional area the whole way up here? Because if we knew that, then we'd have a relationship between Z and the volume anyways, and then since we have the density, we could find a relationship with the mass. Right now we have three things that are independent of each other. I don't think there's another way to do it unless you know something about the Okay, so this whole thing is a cylinder. And so the cross-sectional area is the same the whole way. And so then the mass is equal to the density times the area times the height. So that's 1,000 times the area, so 0.3 Z. And so then we have ddt of 0.3 Z is equal to negative 1.3288 z to the 1/2. And we can divide both sides by 0.3. What's negative 1.3288 divided by 0.3? Divide. That would, so it should be bigger than this. (1.3288) divided by 0.3. 4 point what? 4295. Okay. I just write numbers till I get tired of writing. And then we have z to the 1/2. Okay. So how do we solve this? Now we can use separation of variables. So we have z to the negative 1/2 is equal to, z to the negative 1/2 dz is equal to negative 4.4295 dt. We have a value for the starting mass. So let's get the starting height. We know that 0.3 z is equal to 2,500 kilograms. And so z is huge. That's not really, well, what's that going to be? 0.8333. That's meters. I don't think anyone makes tanks like that. If this is the way that this is supposed to be done, then you do the integration. That's your starting value of z. So you'd say like, oh, and you can also get the final value of z that way. So 0.3 z is equal to 900 kilograms. And so this would be like z1 is 8333, z2 would be 3000. And so now we can do this integration. So integrate z to the negative 1/2 dz from 8333 to 3000. And that's equal to negative 4.4295 t. So we get z to the positive 1/2 over negative 1/2, so negative 2 be negative. Evaluated from 8333 to 3000. So what do you get for the left side? It doesn't. Negative 73.02, okay, is equal to negative 4.4295. So what's T? 68? 16. 6.48 seconds. Okay, well, I don't think there's any other way to do that problem. I should look back and I'll bet I just left a sentence out of that question or something. But what you're trying to do, the overall picture is you're trying to use, you know that your sort of governing equation is going to come from conservation of mass. And you're using their other relationships to plug stuff into your governing equation to the point that you can solve it. Any questions about that? Any other homework questions? Okay. I'm not going to start a new topic really, but I'm just going to start. I'm going to say something about it, and then we'll get into it after the test. But the next topic is the first law of thermodynamics for control volumes. And just like conservation of mass for control volumes, our system will be a material inside the chosen volume at each instant. And so what that means is that at different instants, your system is different collections of particles, different collections of this material. And so what we're going to have to do is account for the fact that when we're looking at one instant, there's material coming in that's carrying energy and enthalpy, and it's carrying that stuff into the system. And at the outlet, that stuff is being carried out of the system. So what we did before with the first law, remember the first law is conservation of energy. Is we said the time, the rate of change, the time rate of change of energy in the system was equal to the rate at which energy was added to the system by heat minus the rate at which energy is removed from the system by work. Okay, so that's the one that we're used to. Now we have to account for the fact that at any instant, material and energy and other stuff is being carried in at the inlet and being carried out at the exit. So for a control volume, what we have is that the time rate of change of energy in the control volume is equal to the rate of, I'm going to shorten this a little, energy into the control volume as heat minus the rate of energy out of the control volume as work. And here, let's say we're going to account for the inlets and the outlets separately. So this is excluding any work done at inlet and exit. Then we're going to, now this is the new thing. Basically, these are all analogous of each other. But now we have to account for the fact that energy carried into the control volume at inlet like if you high temperature liquid coming in at the inlet is adding energy to your control volume minus energy carried out of the control volume at the exit. And we're going to see, and I'm going to go through this derivation next time. It's not horribly long or anything. We'll see that enthalpy and remember enthalpy is equal to the total internal energy plus the pressure times the volume. And if you do it, oh, if you do it as a specific, if you do it on a per mass basis, specific enthalpy is equal to specific internal energy plus P specific volume. No problem. Those arise from energy going in and out of the control volume as work. Okay, so this enthalpy thing, I said before, there's kind of a rough hand-wavy interpretation of what enthalpy is. You can think of it as the internal energy in some material plus the energy that it would take to make space for it in its surroundings. Still, like an idea like that, like why would that ever be useful? The real answer for what enthalpy is it's kind of like a mathematical artifact that comes about when you use the first law for a control volume. And so I'm going to go through the derivation. You're going to see where that comes from and how much do I want you to get out of the derivation. I think every minute you spend following like careful mathematical derivations is good, but for this class, I would say the main thing I want you to remember is that if you go through the derivation of the first law for a control volume, that's where this idea of enthalpy pops out of. It's a mathematical thing that pops out of this derivation. Okay, and that's about it as far as this class goes. As far as like your overall kind of mathematical comfort or whatever, every proof or whatever, every derivation has little things that'll be useful in the future. So I always think it's good. I know I used to, like when I was in college, oh my God, you guys are popular today. I sort of had a bad habit in math classes. Like I was a math major and all my classes were like proofs, and I'd sort of be like, the teacher would start a proof and I'd just be like, okay, well, I already know what the theorem is. And then I'd just be like, do, 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 until she was done, or whatever. But it's watching, trying to understand the steps of that kind of stuff. It's a good idea, Otherwise, you're just sitting here doing nothing. Okay, anybody have any questions about this? I'll go into that on Thursday, a week from Thursday. Our next class is Tuesday, and that's the test. All right.